On April 1st, 2026, for the first time in more than half a century, human beings left low Earth orbit and returned to deep space. The Artemis II mission rose from Earth atop the most powerful rocket of the modern era, carrying astronauts on a path that would take them around the moon and back. It marked a moment many believed might never come again. A quiet but profound return to a place humanity had not touched since the early 1970s. And yet, almost immediately, a question begins to form. If we were able to send humans to the moon in 1969, if we landed, explored, and returned safely, why has it taken more than 53 years to come back? Why does something that once seemed possible now feel so distant, so complex, and so uncertain? The timeline itself is precise. The last human footprints on the moon were left in December 1972 during the Apollo 17 mission. Since that moment, no human has stood on the lunar surface again. Now, in 2026, Artemis II carries astronauts back into deep space. More than 53 years have passed since humans last walked on the moon. But there is an important distinction that is often overlooked. Artemis II is not a return to the lunar surface. It is a journey around the moon, a test of systems, a confirmation that humans can once again travel safely beyond Earth orbit. It proves that the path back is reopening, but it does not yet mean we have arrived. And so the real question is no longer whether we can return to the moon, it is why. After more than half a century of progress, we still haven't. If we follow that question honestly, we begin with a simple assumption that feels almost impossible to challenge. We have already been to the moon. The engineering worked. The mission succeeded. So returning should simply be a matter of doing it again. But that assumption contains a subtle mistake. It treats Apollo as if it were a permanent capability. Something humanity built, verified, and then stored away, ready to be used again when needed. As if going to the moon were like following a recipe that has already been perfected. The reality is almost the opposite. Apollo was not a system designed to be repeated. It was a system designed to achieve a single objective under extraordinary conditions. Once that objective was complete, the system itself began to disappear. To understand why, we have to step outside the technology and look at the moment in history that made Apollo possible. Because Apollo was not just an engineering project. It was a response to something much larger. In the late 1950s and early 1960s, the world was divided by the Cold War. The United States and the Soviet Union were competing not only in military power, but in technological prestige. Each achievement in space was seen as proof of which system would define the future. The moon became the ultimate stage for that competition. It offered something no other achievement could provide. A single, undeniable demonstration of technological dominance, visible to the entire planet. This context changes everything. Apollo was not built because it was efficient, or sustainable, or even practical in the long term. It was built because it needed to succeed, quickly and decisively, and that urgency translated directly into resources. At its peak, NASA consumed roughly 4.5% of the entire United States federal budget. In today's terms, that would be on the order of hundreds of billions of dollars. Today, NASA operates with less than half of 1% of that same budget. The difference is not small. It represents a gap of roughly 6 to 8 times in national investment. This leads to a difficult but essential realization. Apollo was not constrained by cost in the way modern programs are. It was not designed to be affordable. It was designed to work, and that distinction matters. Because once the political objective was achieved, once the moon had served its purpose, the funding, the urgency, and the entire structure that supported Apollo began to fade. Apollo, in that sense, was a sprint, a powerful, focused effort that reached its destination with extraordinary speed, but was never intended to continue indefinitely. And if that is true, then a more important question begins to emerge. If Apollo was not meant to last, if it was never built to be repeated, then what exactly did we lose when it ended? The idea that we simply lost the technology to go to the moon is often repeated, and it sounds convincing at first, but it is not quite accurate. The physics has not changed. The equations still work. We still know how rockets function. What changed is something far less visible and far more difficult to rebuild. When Apollo ended, the capability to reach the moon did not go into storage. It was not preserved as a complete system waiting to be restarted. Instead, it was gradually dismantled. The Saturn V rockets stopped being produced. The factories that built them were repurposed. The specialized tools, the manufacturing processes, and the supply chains that supported them began to disappear. What remained were documents, blueprints, and archive data. But complex systems are not built from documents alone. There is always a gap between what is written down and what is actually done. This is where a more subtle form of knowledge becomes important. Engineers sometimes refer to it as tacit knowledge. It is the understanding that cannot be fully written down. It lives in experience, in intuition, in the small decisions made during thousands of hours of work. A blueprint can describe a component with perfect precision, but it cannot fully capture how that component was actually built, tested, and refined over time. The real system exists not only in the design, but in the people who know how to make it work. At its peak, the Apollo program involved more than 400,000 people across thousands of organizations. Engineers, technicians, machinists, and operators formed a vast and interconnected workforce. Together, they held the practical knowledge required to turn theory into reality. When the program ended, that workforce did not remain in place. It dispersed. People moved into other industries, other roles, other priorities. Over time, the shared experience that once connected them faded. There was no continuous line of succession, no generation trained directly to replace the one before it. The chain of knowledge, once broken, could not simply be restored by reopening old designs. In the decades that followed, attempts were made to rebuild deep space capability. Programs were proposed, funded, and in some cases partially developed, but many of them were later cancelled or restructured as political priorities shifted. Each time, progress slowed, and teams were forced to start again from a different point. Over time, this created a pattern, not of steady progress, but of repeated resets. Knowledge was gained, then partially lost. Experience was built, then dispersed. Momentum never had time to fully accumulate. This is the hidden loss that followed Apollo. Not a single technology, but an entire ecosystem that once knew how to build, integrate, and operate a system capable of reaching the moon. And this changes how we should think about Artemis. It is not simply continuing where Apollo left off. In many practical ways, it is rebuilding that capability from the ground up, within a world that is more complex, more constrained, and more interconnected than before. Up to this point, it might still feel like something is missing. We had the technology, we had the knowledge, we reached the moon. So why does returning now seem more difficult? Not less. The answer begins with a simple but critical shift. The mission itself has changed. Apollo and Artemis may share the same destination, but they do not share the same purpose. Apollo was designed for brief visit, land, explore for a short time, and return. Artemis is being designed for something entirely different. Not just to reach the moon, but to remain there for longer periods, and eventually to build a sustained human presence. That difference may sound subtle, but it changes everything. A mission that lasts a few days can rely on tightly constrained systems. A mission that lasts weeks or months must account for failure, redundancy, and long-term survival. What worked for Apollo does not simply scale upward. This creates what engineers often describe as a scaling problem. During Apollo, astronauts spent at most a few days on the lunar surface. Artemis missions aim to extend that to weeks, and eventually much longer. As time increases, every requirement expands with it. Life support, power, thermal control, and reliability all become more demanding. At the same time, our understanding of the lunar environment has deepened. We now know far more about the risks than we did in the 1960s. The moon is not just distant, it is hostile in ways that are difficult to fully appreciate from Earth. Radiation is one of those risks. Without a protective atmosphere or magnetic field, the lunar surface is constantly exposed to high-energy particles from space. During Apollo, missions were short enough that this exposure remained within acceptable limits. Over longer durations, it becomes a central challenge that must be actively managed. Lunar dust presents another problem. It is fine, abrasive, and persistent. Apollo astronauts experienced its effects even during short missions. Over extended stays, it can damage equipment, interfere with systems, and pose potential health risks. Then there are the thermal extremes. The lunar surface experiences dramatic swings in temperature, from intense heat in sunlight to extreme cold in darkness. Apollo missions were carefully timed to avoid the most severe conditions. Long-duration missions cannot rely on such narrow windows. These factors lead to a deeper requirement to stay on the moon. Humans must build infrastructure, reliable sources of power, protected habitats, systems to recycle air and water, and eventually the ability to use local resources. This is no longer a question of reaching the surface. It is a question of living there, and that is the fundamental shift. The difficulty has not increased because the moon is harder to reach. The difficulty has increased because our expectations have changed. We are no longer trying to visit. We are trying to stay, which leads to the central realization behind everything we have explored so far. The moon is not harder to reach than it was before, but staying there, safely and sustainably, is a far more complex challenge than anything Apollo was ever designed to solve. Artemis II, in many ways, is a quiet kind of success. It does not place human footprints on the moon. It does not build habitats or establish a permanent presence, but it proves something that had not been demonstrated for more than 50 years. Humans can once again travel beyond low Earth orbit, operate safely in deep space, and return home. The Space Launch System has demonstrated its ability to deliver crew beyond Earth orbit. The Orion spacecraft has shown that it can sustain human life during that journey. Together, they represent the first step in rebuilding a capability that has been absent for generations. And yet, this success does not resolve the larger challenge. Artemis II does not land. It does not address long-term survival on the lunar surface. It does not solve the problem of cost, or the question of how often such missions can be repeated. In many ways, it confirms that the journey has begun, but not that it has been completed, which brings us back to the central question. The reason humans have not returned to the moon for more than 53 years is not a lack of knowledge. It is not a failure of science. It is the absence of a very specific set of conditions that once made Apollo possible. Apollo was driven by political urgency, funded at levels rarely seen in peacetime, and built within a culture that accepted levels of risk that would be difficult to justify today. Remove any one of those factors, and the program would likely have unfolded very differently. Remove all of them, and it becomes almost impossible to repeat in the same form. Artemis exists within a different reality. It is not trying to recreate Apollo. It is attempting something more difficult: to build a system that can return not once, but repeatedly, not briefly, but for longer durations, not at any cost, but within limits that can be sustained over time. This is a slower path, a more complex path, and at times, a more uncertain one. But it may also be the only path that leads beyond a single achievement toward a lasting human presence beyond Earth. The next step in that journey is expected to come with Artemis II, a mission that aims to return astronauts to the lunar surface, not just to visit, but to begin testing the systems that could support longer stays. It represents not a repetition of the past, but the first attempt to build the future. And so the question is no longer whether we can return to the moon. Artemis II suggests that we can. The deeper question is what happens next. Whether this time we can stay.